Well, hello, friends. Today we're going to work on the profiler again, and specifically we're going to make tree inversion in the profiler. So what that means is, well, actually, let me grab a profile before I say too much. So what are we going to profile? How about we grab a text editor and we open the Serenity README. And as you can see, we have this line wrapping turned on here. Maybe we want to profile that a little bit, see what it's spending its time doing. So let's see, we have text editor here. So profile process 18. We'll resize it a little bit like that. Put some stress on the line wrapping, and then we will save this into TE. So let's bring up the profile. So as you can see here, by the way, new since last time is now the samples are scaled according to their stack depth, and it's kind of a nice suggestion from Tibor. And also I've spent a little time optimizing this so that selecting here is just fast instead of being laggy like it was before. But anyway, let's just take a quick look at what it's doing. So by the way, tree inversion, what I mean by that is right now the tree is root first, and in profilers it's often very useful if you can flip the tree around so that you have the leaf as the root, and then you would find you would have to like open this up and you would like travel backwards until you get this instead. And what that tends to do is that it exposes things that are often found very deep in the call stacks, but like if you end up in the same place very commonly, just you take different paths there, then if you start with the root, then it's not as obvious. Say that, for instance, we're hitting a lot of page faults, right? And maybe if I open up these guys here, see, I found more page faults. Now, this one here has 37 samples in it, and this one has 5. But if we would flip the tree around, we would notice that actually that adds up to 42 in the page fault entry or page fault handler. So it's just a way to surface a different aspect of the profiling information that tells you like, well, in this particular function, you spend this much time in total, even if you took a different path to get there every time, or well, not every time, but you know. Anyways, if you're familiar with profilers, then you know all this already. But if you're not familiar, I definitely hope that maybe watching this would inspire you to learn more about profiling, because it's absolutely awesome. So anyway, let's make sure that we save this profile, and then we will work on inverting the tree. So what is it that I want to do? Mount disk image, mount home and on to. It's home and on to, or yeah, to it's fine. And you mount base home and on to. Okay. Cool. So now, first thing I guess is we'll have to add some kind of a mode for this. So let's go in profile viewer main. We'll just add a menu for this. I'll call it like view menu, something like that. View. Add action, and we'll say invert tree. Maybe we will have a hotkey for it. How about Control I? Control I, it's pretty good. And when this gets called, actually, maybe we should make this. We'll make an action object for this. menu, add action, invert action, because I think we are gonna make this checkable. Checkable true, invert action, set checked true. We'll start in this mode. Set checked action not checked, and then I guess we want to flip everything around. So we got to tell the profile that he's supposed to show himself upside down. And that really happens in the profile model. So where do we have that? We don't really have that anywhere. Okay. We'll just say set profile, set inverted action is checked. Wait, hold on. Yeah, right. Set check true, set inverted true, okay. And set inverted. Ooh. Okay, and then how is this going to work? I guess we'll just generate the tree in the other direction. So instead of starting at the root every time we investigate a sample, we would just start from the innermost stack frame instead. I guess that would make sense. Then let's see. So here, wait, what am I thinking about? This, by the way, is how I made the selecting the time range go fast. I just now instead of looking at JSON data every time that we are regenerating the tree, we fetch the JSON data once in the constructor of a profile, and then we convert it into these native storage. Like we store U32 instead of JSON value, and we store the symbols as strings and so on. And this ends up making things so much faster because just going in and out of the JSON types is not efficient compared to native storage. Although there's a lot of room for improvement in the JSON framework, but this seemed like the appropriate solution at the moment. So in rebuild tree, I guess here's where we want to look at if it's inverted or not. So is it here, basically, where we iterate the samples? So maybe we'll make a, wait, hold on. Here we iterate over the samples, and then here we iterate the frames in an individual sample. So maybe we can make something like, because we want to loop differently depending on if it's inverted or not. So for each sample, is it possible to do something like this? Type name, callback, if m inverted, do this. Callback of sample frames at I, else start at sample frames size -1, go backwards like that, and then we would write like And const sample frame. It's not for each sample, it's for each frame. Andreas. So for each stack frame, do that, and this would have to return. Wait, break. What is that breaking out of? Oh yeah. So the stack ends there, right? So return. I guess we can use an iteration decision. So if callback is iteration decision break, then break. Something like that. And actually, this is the not inverted version. And okay, and here we want to iteration decision break. Otherwise, we want to return iteration decision continue. Okay. So, am I doing this remotely right? That's not how you do that. Yeah, I had a feeling that was not it. What about this? Template declaration cannot appear at block scope. But I've seen this before. It's in the thread code. Type name. Yeah, here. Oh, you put the captures first. Right. I think Clang doesn't like this. But GCC does. That's nifty. Okay, set inverted, not implemented. Oh, I'm sorry. If m inverted is inverted, then no op. Otherwise, inverted is inverted, rebuild tree. All right. Okay, we are empty. That's not good. If we invert, then at least we have our stack frames. Oh, and the menu. I forgot to add it to the menu bar. But we're empty. That's not a good sign. Menu bar dot add menu. Move view menu. All right. Almost. So why are we empty? I bet that we are hitting that break sooner than we would like, because as I recall, there is some garbage in each sample. Like, yeah, here. So check it out. The first frame of every sample is some crap that we don't want. So I think because now that will be the first one we visit with an empty symbol. Previously, we were going from the back of the sample, so like always starting at the outermost stack frame, and then working our way up, and then breaking out when we hit this one. But now we start here, so we break immediately. I don't know what this one is really, by the way. I guess it's just the stack frame pointer when we're starting out. Maybe it's just the stack frame pointer value at the moment. So this would be like a stack address, which makes it completely useless to us, but, oh, hold on. Ah! Yeah, looks like it could conceivably be a stack address. Anyway, we gotta ignore that, so, but it's always the first one. So when we're inverted, wait, hold on a moment. We're going from, wait, are these in order or what? Oh shit, no, hold on. When we generate the profile, when we do this conversion that I mentioned, we go backwards. So we convert from the JSON. So actually, in the array that we've produced now, this one is the first. So that's what we're doing here. We're converting the JSON to C++ object. So this is already done backwards. Maybe we could just skip over this element then. We can do that. And we won't include it. Okay, let's try that. That means that, what does that mean? When we iterate, if we're not inverted, then we'll just do the samples in order, which means the root will be first. If you are inverted, you gotta do them backwards, which means that the, okay, yeah, I think maybe this will just work actually, now that we actually filter out the unwanted stack frame in the beginning there. Okay, so I think we've just inverted the graph. Now, these are not sorted anymore. That's a bit annoying. But we can see that the stacks now go from the innermost stack frame to the outermost. And here's page fault handler. Look at that, 113 samples. It's quite many. Very interesting. But why are they not sorted anymore? Root, sort children. We're not sorting the roots though. We need to sort the roots. What does this code do? Oh, okay. Wait, sort children. This is just operating on one of these guys. So technically we could probably just have, or let's just sort them. Sort the roots. Sort roots. Okay, does that work? Non-pointer type profile node, shit. Wait, is this gonna work? No, that does not work. Why not? Swap, right, yeah, we can't swap. This is a stupid problem. We can't use non-null ref footer vector because it doesn't support quicksort. The quicksort algorithm doesn't know how to handle non-null ref footer vector. So we gotta use a regular vector of non-null ref footer. Then we're good. Too many ends. Too many ends, and then we have to use an arrow instead of a dot. The horror. Of course, use these guys here also. And so I guess we should probably separate this out in some kind of a helper. Sort profile nodes, roots, and profile nodes and children. And we'll just make a helper for this instead. Vector, non-null ref footer, nodes. So first sort among our siblings and then sort our children. And look at that. We are now upside down and sorted by sample count. That is just so cool. Because now you can see that the page fault actually dominates this profile if you flip it around. Because if you turn it up this way, damn it, what happened? I pressed the left key in the tree view and it crashed. Okay, we're gonna have to fix that, but we'll do that separately. I just want to illustrate that if we open up this profile here, right, it's not immediately visible that the single most time spending thing, or the place where we spend the most time is in the page fault handler. You have to actually do a little bit of mental math and like look at all these to discover that. But if you just flip it around, you'll notice it right away. The page fault handler is on top. Very, very handy. And then when you turn around, instead of so what you now see is basically who's responsible for triggering all these page faults, and that will be gwindow event mostly. And I think in that case, it's probably because that's where window painting is initiated. So I was resizing a lot while making this profile, right? Resizing the window over and over. And what ends up happening then is we keep allocating new backing storage for the window. And the result of that is that we get this big allocations from the kernel to put a new bitmap into. And all of those, whenever we start rendering the window, then we trigger these zero faults in the kernel, which just allocates a page and fills it with zeros. So that's probably what we're seeing here. It would be possible, actually, probably to make this even better by somehow like getting the kernel to have one more stack frame where we call the appropriate type of fault handler, so that you could see that these are zero faults. But that would require rearranging the page fault code a little bit. But this is very cool. So just out of curiosity, what else can we see here? This is the paint event. So yeah, so this is, by the way, one thing that when you flip the tree around like this, then obviously you're going to get the same stuff many times, because every innermost frame will have its own entry now. So gwindow event, if we look here, this is, or where are we? Handle paint event. This guy right here. He also occurs down here. So a fair amount of time spent in this function as well. Likewise here. So very interesting. This syscall, called quite often. Shared buffer, we use shared buffers for the window backing storage. So obviously they cost money to use. What is this? Oh, this is freeing the IPC message that we're sending to the Windows server. Fair amount of time spending freeing those message buffers. We can definitely improve that. It's something I've mentioned before. But you know, one thing that's kind of lost right now, since we don't have any number for perspective, but like how much of the total profile is this really? We don't see that right now. If we flip it around, we see that the total profile is 724 samples. So this is like, I guess, like, let's say a seventh, right, of the profile. But I'm not good at mental math either. So what is it really? 113 out of 724. Wait, can I get a bigger scale? 15%. And what is that exactly? 100 divided by 15. Yeah, 166. Anyway, so it's not a huge chunk of the profile, but it is the most dominant thing. This is very useful if you want to go and micro-optimize something, because this will surface things that you can micro-optimize. Anyway, profiling is very fun. Something I love to do. So I'm very, very thrilled to finally have the ability to turn the tree upside down, because whenever I'm profiling, that's always something I want to do. So let's commit this, and then let's look at that crash we had when I pressed the left arrow on the keyboard. There's nothing crazy going on here, right? So profile viewer. The ability to invert the profile tree. We should call it a graph, I guess. Or invert the profile tree. Is it a graph or a tree? Yeah, let's just call it a tree. Inverting the tree puts all of the innermost stack frames, turns all of the innermost stack frames into roots, allowing you to explore them, allowing them to accumulate their total sample counts. With other instances of the same frame being innermost. This is very useful for profiling. This is an essential feature of any cool profiler, and now we have it. Cool. All right. This is so much fun. Oh my gosh. I don't know. I mean, everything is fun, but this is so much fun too. It's just great. So the key press, right? So tree view, key left. You jerk, why do you crash? Let's get that crash trace. So, oh shit, we should turn off this mode by default, by the way, because we want the profile to look like this by default. So we try to go left, doesn't happen. Wait, but how do I get it to go wrong again? Is it, no, it's not crashing. Crap. Okay. Oh, there we go. If I don't have a valid index, maybe that's it. So what was our call? Stack key down event, and then ensure metadata for index. So if the cursor index is invalid, then cursor index, we're just comparing it in these cases. And here, oh, so maybe it's always gonna crash on us if you press the left or right keys when you don't have a selected item. So left crashy and right crashy. All right, well that is easy. So we'll just say if cursor index is valid and it's always good to fix crashes. Don't want to have those. Okay, so flip it around, left and right, working just fine. You can go down, start browsing. Very cool. Okay, awesome. So, libgui, fix gtree view, crashing when pressing left, right key without selection. Damn it, it's not gonna fit. Crash. Here we go. And let's make sure profile viewer doesn't start in inverted mode because I don't want that. Okay, we are looking so good. That's so cool. I love this program. Very, very awesome. Okay, and then of course we can switch like this. Cool, 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 cool. I think we will put this in a squashed. We'll squash this into the this commit right here. because this doesn't have to be its own commit. Okay, so it goes into that one. All right, so I think this is going to be it for today's video. So if you made it this far, then I thank you for hanging out. And I hope you saw something interesting, and I hope you are just a tiny bit excited about profiling, because if you're just 1% as excited about profiling as I am, then you are going to discover interesting things about your programs and stuff. But yeah, this is going pretty well so far with this program. I freaking love it. So let's turn it around. I like that it also works with time range filtering. It's too good. Yeah. I just want to sit here all day and just profile everything, but there's more things to life than profiling, like writing profilers, for example. Profiling your profiler. Anyway, thanks for hanging out, and I hope you saw some interesting stuff. I will see you next time. Have a great day. Goodbye.